So we're kind of to the point now where we're just picking and choosing the topics that we have not got to cover yet that need to be covered to complete a pre-cal class. And the first of those is here in a complex plane. This goes very nicely with vectors, so that's why it's done right after vectors. But if we read here, it says, just as real numbers can be represented by points on a number line, you can represent a complex number as a point on a complex plane. So that sounds real fancy. You're fixing to be graphing on the complex plane. Ooh. So complex plane is made up of real numbers and imaginary numbers. Right, just like a complex number is. How did we get imaginary numbers in the first place? Taking a square root of a negative number is what gives us a negative, or what gives us an imaginary number to start with. So you see how this kind of ties back to what we were doing previously, but now we're going to apply it with vectors, knowing what we know there. So usually on our coordinate plane, we have what's called the x-axis and the y-axis. But on a complex plane, we have a real axis and an imaginary axis. The real axis is the horizontal axis that goes left to right, like what an x-axis usually does. And the imaginary axis goes up and down, like what a y-axis does. Vertically. You can see here they have several points on their complex plane. Notice the point 3, 2. What does that represent? That represents a real part of 3 and imaginary part of 2. So we could write that as the complex number 3 plus 2i. You kind of see how this goes with coordinate plane, x and y. You kind of see how this goes with vectors, with your I hat and j hat, right? How you have an x component and a y component. Here you have a real component and an imaginary component that you're plotting on the axis. Look at this one, -1, 3. That means the real part is -1. The imaginary part is a +3. All right, next thing we're going to do is talk about the absolute value or the modulus of a complex number, a plus bi. I'm not really sure why this is considered a modulus, but it is what it is. So let's think about, how do you find the absolute value of a real number? Like if I ask you for the absolute value of -5, the answer is 5. If I ask you for the absolute value of 3, the answer is 3. So you learned a very specific way of how to find the absolute value of something. Would it surprise you if I told you there's a more complicated way that works even in this case as well? The way we find the absolute value is by using the distance formula. Because what did the absolute value represent? The distance away from 0. Right, that's what they told you when you first learned about absolute value. The absolute value of -2 means that number is 2 units away from 0. So its distance was 2. So the absolute value was 2. So like, think about, for instance, this number. If I had the number 5 plus 0i. I wrote my I backwards. 5 plus 0i. What's my real part? 5. What's my imaginary part? 0. So we could rewrite this as just being 5. Right? Well, what's the absolute value of 5? Well, we know that's 5. But what if we didn't know and we had to use the distance formula? What's the real part? 5 squared. What's the imaginary part? 0 squared. So what would that give me? The square root of 5 squared, which is 25. What's the square root of 25? So you can still find the absolute value of any number using the distance formula, not just a complex number. It works for real numbers as well. Obviously, you don't have to do it with just a real number, but you're going to have to do it with a complex number. Okay, so here I want to plot the point z at -2 plus 5i, and I want to also find its absolute value. So let me find my coordinate plane. It's been a while since I've had to use it. There it is. Okay, so remember, my x-axis represents my real part. So in this number, the real part is -2. The imaginary part is 5. That means I'm going to go left 2, up 5. And right there would be my point Z. And look what you've done. You've now graphed on the complex plane. Don't you feel so smart? Next part, find the absolute value. So what is the absolute value of -2 plus 5i? Well, the way we find, oh my gosh, it's delayed. The way we find the absolute value of a complex number is we plug into the distance formula. So this would be -2 squared plus 5 squared. We drop the I. Do not put the I inside your distance formula. -2 squared is 4. 5 squared is 25. So this is radical 29, which does not simplify. So the the absolute value of -2 plus 5i is radical 29. So if we think about it, where is that distance? Like, how can I see distance on this graph? Well, if I go from the origin to that point, right, that's a distance of radical 29. Right, if you were to draw a straight line from the origin to that point. Because what do you have? You have a right triangle, where this value is the x value. This value is your y value, or your imaginary part. And you could just say this squared plus this squared, then take a square root to find that distance, right? The distance formula just comes from the Pythagorean theorem. Okay, so the point would be at 3, -4. So your point should be here. Right, this is your point Z. Any questions about that? And then what is your absolute value? 5? No, it is not radical 17. Oh, it is a 3, 4, 5 Pythagorean triple. Oh, who would have known? Oh, yeah. So what do you put under the radical? 3 squared plus -4 squared. Yeah, so what did you get for 3 squared? 9. 4 squared. That's 16. So it would be radical 25, which is 5. Remember, -4 squared is not -4 times 2. It's -4 times itself. Okay, so in 6.3, we learned how to add and subtract vectors geometrically in the coordinate plane. So we didn't do a lot of that. We ended up just combining the x components and the y components. But if you'll remember, I showed you once how you can just line up a vector from nose to tail, right? If you're adding u, it's like for instance here, here, they're adding u, vector u, and vector v. What they do is they move vector v to put its to put its initial point for V on the terminal point for U. We're basically sliding vector V up so that it begins where U ends. And you see how you have vector U and vector V, and that gives U plus V. That's what we're doing when we add vectors geometrically. Can y'all see, or am I in the way? So again, a complex number Z, which is written as A plus BI, can be represented by the vector U in the coordinate system AB. For instance, 6.32, the complex number Z, which is 1 plus 2i, is represented by the vector U. So if I looked at this vector U, and I knew I was in the complex plane, right, real part and imaginary part, I know this represents a complex number. If I'm going to add two complex numbers, I add the real parts and I add the imaginary parts. Or I stack them right in the complex plane as shown. So this here is one of your standards. For pre-cal, you have to be able to do this geometrically. So I'm going to show you how to do it geometrically, and I'm going to show you how you can verify it algebraically. So if I had to add 1 plus 3i, so I would go to 1, 3, which is here. That's going to give me my first vector, which is 1 plus 3i. Right, it begins at the origin, it ends at 1, 3. Now the second vector I'm adding is 2, 1. So that vector in the standard position would look like this. What's in green? Right? If I take that vector, see if I can make it be disconnected. That would be very nice. Of course I can't. So here's the vector 2 plus I, right? Real part's 2, imaginary part's 1. What I would do is I would take this vector and I would move it from here to put its initial point at the terminal point of the previous vector. So now I've added the two vectors. I put one stacked at the end of the other. How could I do that if I couldn't move it around? Well, from here, what could I do? Go right 2, up 1. Right, that tells me where that vector should go because this is its x component and its y component. So what does the final answer look like geometrically? It would be this vector, starting at the origin and ending at 3, 4. That's my answer. Is it simple enough? Now, how could I know what this is algebraically? Well, just add the real parts. What are the real parts? 1 and 2. That means my real axis should go all the way to 3. What's my imaginary parts? 3 and 1, which means my imaginary axis should go to 4. Right? So that's how you do it algebraically, but you have to be able to represent it geometrically because that is the standard. Questions? Okay, so here, if you added 3 plus I, geometrically that should look like this. Right? It went to 3I. The next one is 1, 2. Because I can't move it if I do. It ties it to I move it all at 1. That's what I learned. So, now this is the vector 1, 2. Right, just look where the arrow ends. All right? And so now if I wanted to find this added geometrically, I could move it to the end of this vector, like so. And again, remember, look, it's where the arrow ends. So my final answer would be here, this vector, which has, I'm wrong, ain't I?
Yep.
Hold on.
That's right.
Y'all know what y'all are talking about. Give me just a second. 1, 2. That's 1, 2. Right, it's there. Okay. Now, if I move that, I made mine 2, 2. Speaking of 2, 2, one of my best friends. Never mind. Okay, here we go.
Clay Cooper.
Clay Cooper's one of my best friends?
So he said 2, 2, and he was double 2s.
Well, this is actually another guy that was double 2s, but it's not Clay Cooper.
Jake Slade.
No, it'd be one of my friends, so that'd be back before their time. Look here. What's my final vector? It has a real part of 4 and an imaginary part of 3. So this would be 4, 3. Okay, so here we are subtracting complex numbers. 4 plus 2i minus 3 minus I. So let me show you geometrically what that looks like. So if I go to 4 plus 2i, it's going to be this vector here. And then 3 minus I get pretty close. Would be this vector here. Okay. Is everybody ready? You're watching?
Yes, sir.
How can I copy? I know there's a way to copy.
Oh, Control C, Control V.
Thanks. Yep. There's no keypad on here, though. Okay. So, when we subtract vectors, what we do is we take the vector and we rotate it 180 degrees in the opposite direction. Because what is a subtraction? That's a negative. Well, what's a negative graphically? That's a reflection. Right? How we would reflect over the x-axis or the y-axis if there was a negative. Well, this time if I'm subtracting, I'm going to reflect it over itself. And so now the vector would look like, what am I supposed to be? 3 minus I. So it would be there, right? That's a 180 degree rotation or a reflection across the origin. And so now graphically, if I'm subtracting, I'm going to put this vector still just like I would if I was adding. Put it right there on the end of the previous vector, and I think I did this correctly. That means that my correct vector would be here. I found that to be what vector? 1, 3? Well, let's look at what happens if I combine these. What is 4 minus 3? 1. What is 2 minus negative 1? Well, minus negative 1 is the same thing as plus 1. So 2 plus 1 is 3. So it still works algebraically just like you think it should. But you have to be able to do it graphically. Right? This is the standard, is being able to draw those vectors. Okay, so 2 minus 4i means this should be your original vector. And if I'm subtracting 1 plus I, normally that goes right 1, up 1. So because I'm subtracting, that means I'm going to go left 1, down 1. So this would be what minus 1 plus I would look like. And so my final vector would be the black one here, which has coordinates of 1, -5. So here's the new one. We're going to find the complex conjugate of -3 plus I. So, does anybody remember, what is a conjugate? Conjugate. What do you mean by opposite? It does have to do with a little bit of opposite.
3i plus 8 and 3i minus 8.
So we changed the sign of the second term. Right? We would change the sign of the imaginary part. So in this problem, -3 plus I, that would be represented by this vector. Right? I went left 3, up 1. Its complex conjugate would be -3 minus I. And that conjugate would look like this. So left or right doesn't change. Right? The only thing that changes is the vertical component. So what does this look like? A reflection over the x-axis, because we're changing the sign of the y component. That's what a complex conjugate graph looks like. Okay, so my point 2 minus 3i is here. So the complex conjugate would be here. Any questions? 2 plus 3i. Plot 2 complex numbers and find the distance between them. So my first complex number is 2 plus 3i. Thanks. 5 minus 2i. Thanks. And I want to know the distance, which would be the length of the line. So how could I find the distance between 2 points? Distance formula. Subtract your x's, or your real parts, square it. Subtract your y's, or your imaginary parts, square them. So everybody knows this is a 3/5 radical 34 Pythagorean triple. Just rolls off the tongue. Okay, I don't know that one. Did I get it right? I did. Any questions?